Welcome back. So we have been discussing about scalar coupling since more than two or three classes. Sorry. Today we'll continue with the multiplicity pattern. Yesterday I showed you what happened to the multiplicity pattern when a hypothetical molecule like this I took. I looked at proton A when it is coupled to Y and CH2 proton, a single proton and its two equivalent protons. I assume the condition AY is larger than AX. That means this coupling is larger than this one. Then first larger splitting is doublet. Then each of them is further split into small couplings of a triplet. And this easily we could say, we could analyze, and this is called doublet of triplets. I told you, please remember, it is called doublets of triplet. Doublet of triplets. Always larger coupling should come first, then smaller couplings. Okay, it is not triplet of doublets, it is doublet of triplets. Okay, so what is the pattern for Y? Remember, in this case, Y, AY is larger than YX. Okay, it should not be X, it should be YX. So now in which case, I told you this is larger coupling AY and this is XY. So when this XY coupling, if you see 1, 2, 3, 4 bonds away, much smaller. Pattern is similar to this. It is also doublet of triplets. Only thing is, in this case, this coupling was slightly larger than this coupling. So this triplet separation becomes much smaller. That's all. But the pattern is doublet of triplets even for this. Okay. Now we'll go further. What happens if we observe proton X? This is another thing. See, we are now looking at proton X. Proton X is coupling with proton A and proton Y. Now we assume the condition this coupling is larger, A and X coupling, than XY. Look at the multiplicity pattern. First, A splits the CH2 protons to this group into a doublet. Okay, this splits into a doublet because this is a larger coupling AX. Then comes XY. XY is also a doublet, but this coupling strength is smaller, you see. So first it is going to be split into a large doublet because of this proton A, and each chain of this doublet is split into further doublets because of coupling with proton Y. This gives rise to JAX or JAX or XY. Alternately, you can take the center of this doublet and measure, you get JAX. Otherwise, take from one peak to another similar peak of the other doublet. Let us say this is left peak of the doublet. Take the left peak of this doublet, measure the separation. That's also same. That also gives you AX coupling. But the smaller separation gives you YX coupling. This point is clear. Now, what do you call this pattern? Previous was doublet of triplets. Now it is doublet of a doublet. One doublet splitting into other one. See, when the same molecule, when I was seeing proton, this one, okay, remember when I was seeing this proton, this was doublet of a triplet. When I saw this proton also, this was doublet of a triplet with a smaller separation for triplet. Now I am looking at this. This is a larger doublet because of this and a smaller doublet because of this. So it's a doublet of doublets. And separations very easily you can measure. This gives you J coupling AX and further splitting gives you JYX. And the center of this multiplicity pattern gives you chemical shift. But remember always, if a particular proton is undergoing multiplicity pattern, always center of that multiplicity pattern is the chemical shift. Corresponding chemical shift is always at the center. Now, what happens to the situation in this case? I took AX is greater than XY. Now what happens if I take AX is greater than AY? Now this is larger than this one. I am looking at A. AX is larger means this is going to be a triplet, large. And then this is split by Y, this proton. What is this proton? It is a single proton. What it should do? It should split this proton, each lane of this triplet into doublet. So it will become like this. First is a large splitting because of AX. This gives you JAX. Now coupling to proton Y. Each line of this doublet, each line of this triplet is going to be a small doublet like this. What is this separation giving me? JAX, this one JAY. What do you call this pattern? Remember, what I said, you should always consider the largest value, largest splitting value. Largest splitting value was triplet here. This splitting strength is larger than this doublet separation. That means this pattern is called triplet of doublets. Remember, earlier it was doublet of triplets, but it is triplet of a doublet, or triplet of doublets. Okay. Now, when a single piece proton is coupled to CH and CH3, what will happen? Same. Now we are considering this proton. Consider a situation AX is larger than AY. AY is larger than AX. When AY splits this, what will happen? This proton splits this into a doublet. Okay, this is single proton. This is single proton. This will split this into a doublet, large doublet, because coupling is larger. Now, this also experiences couplings with CH3 protons. Now it is equivalent protons. Apply 2Na+1 rule. What are you going to see? This will be 2Na+1. Say this means it will split this line, each of this doublet into a quartet because of this. You understood 2Na+1 how methyl group splits. We have already discussed several times. Okay. Now each line of this is going to split into a quartet. What is this quartet separation? This separation gives me AX coupling, and the center of this quartet or center of this quartet gives you JAY. Okay, this is what it is. Or from center to center, a particular line of this one to this, this to this, this to this, this to this, doesn't matter. Identical line of each of the quartet if you take and measure the separation, that also gives you JAY. Okay, so this is AX, that is AY. Very easily understood. Now, what do you call this pattern? Largest splitting is doublet. Smaller splitting is a quartet. It should be called doublet of quartets. Now, consider a situation AX is greater than AY. That means this coupling is larger. So, quartet coupling is larger. What this adjacent lines of the quartet, what does it give? JAX. Remember, I am concentrating on this proton. This proton is split into a quartet because of CH3 protons. As a consequence, you got a quartet. Now, each line of this quartet is split into a doublet because of this proton. So, this can experience coupling to this and coupling to this. This will give you a quartet. This will give you each line of the quartet into a doublet. So you are going to get a pattern like this. This is AX, this is AY it gives. What do you call this pattern? What is the largest coupling? Largest coupling is a quartet. And the smallest coupling is a doublet. It is called a quartet of doublets. Remember, it is called quartets of doublets. So you can keep on extending the logic. Some one or two coupling patterns which you routinely use, I will tell you. Now, I have removed this single proton, I put as a CH2. What do you call this now? Look at this one. I consider the situation AY is larger than AX. This is a condition I am taking. Then what will happen to this proton when it is split by CH2 protons? This is equivalent protons. Apply 2Na+1 rule. There are two protons. So this will become a triplet with an intensity 1:2:1. Now, this also experiences coupling with methyl group. So, these three protons, equivalent protons, split this or each line of this triplet into quartet again. This will become, first one is a larger coupling. This is JAY, this is JYY. This is quartet, this is a smaller coupling. This gives you AX coupling. What do you call this one? Pattern? What is the larger coupling? Triplet. Smaller coupling? is a quartet. So it is called triplet of a quartets. Triplet of quartets. So it is called triplet of quartets. On the other hand, I'll reverse the situation. Now, this coupling is larger. Let us say AS coupling is larger than AY. What happens? This proton is split into this one larger coupling by CH3 into a quartet. Correct? So this is equivalent protons, 2Na plus 1 rule. This will become a quartet. Now each line of this quartet will be split into triplet because of this. What will become? Now this separation, larger separation gives you JAX, each will be a triplet, and this will give you AX, and the smaller separation gives you AY coupling. What do you call this pattern? Larger is quartet, smaller separation is triplet. It is called quartet of triplets. Remember, it is called quartet of triplets. And as always, I tell you, the center of the multiplicity pattern gives you chemical sheet for the particular proton. Now I am seeing this proton and I am going to get a chemical sheet of A. Let us go into a situation like this. For the same molecule, I will ask you a simple question. I look at this one. What I am going to get? I have not drawn the stick plot. Let us try to understand. I will pose a question to all of you. If I look for this one, what is going to happen? Remember, this coupling is larger. Now, of course, I have to worry about this coupling. This coupling is larger than this coupling. AY is larger than XY. In which situation what happens? This will first become a doublet because of this large doublet. And each line of the doublet will split into quartets. It is called doublet of quartets. Remember, it is called doublet of quartets. On the other hand, I look for this methyl group. What will happen? Larger coupling, let us say, is AX, then XY. This will become a doublet because of this. And each line of this doublet is a triplet because of this. You get doublet of triplets. See the pattern? If you look at this one, it is quartet of triplets. If you look at this one, it is doublet of quartets. If you look at this one, it is doublet of triplets. You see, in the same molecule, depending upon the proton you are looking at, and depending upon the number of equivalent protons it is coupled to, and the coupling strengths, you can arrive at the pattern, whether what type of pattern it is, and give a name for it. And name for this is quartet of triplets accordingly. Okay. Next, another simple example. I am taking an example of a molecule where CH proton is coupled to two CH3 protons of different strengths. When they were equal, we saw what happens, septate, extate, everything, sextate we observed. Now, there are different couplings. First, AY is larger. Because AY is larger, is a quartet. AY is larger. So, what the separation will give you? JAY. Now, each line of this quartet is split into further quartets because of this coupling. What is going to happen now? See, remember, when they see that so now this is one quartet, this is another quartet, and another quartet. So how many quartets you got? 4 quartets. So what do you call this pattern? Large coupling is quartet, small coupling is also quartet. So it is called quartet of quartets. Quartets of a quartet. So now common first order splitting among all the weakly coupled spins, many of them you have understood. Okay. Now I consider a situation like this. They are not equivalent group, they are different protons. A, M and X. What you will get? A will split into X and M because we observe the same X pattern. It is doublet of a doublet. Each proton will be doublet of a doublet. This is doublet of doublet. This is doublet of doublet. This is doublet of doublet. But remember, intensities are same here. Unlike equivalent spins where you get triplet, quartets, etc. When all are in single protons, they will be of equal intensity and you get a pattern like this. Then you simply start calling doublet of a doublet, doublet of doublet of a doublet, doublet of doublet of doublet. Like that, keep on. Okay. Now, one proton is coupled to more than 2 different protons of different protein. Let us take the example. Now this is the situation. One proton is coupled hypothetical molecule X, Y and M. I'm looking at proton A which is highlighted. So what are you going to see? If I see this one, I'm going to see, I put a condition. AM is larger than AX, larger than AY. Just a condition I'm putting. Now look at the spectrum. First, A will become a doublet because of AM, and then each line of this becomes a doublet because of AX, and now we get doublet of doublet of doublet of equal intensity because of AY coupling. This we observed. Last time we discussed a couple of 1 or 2 classes before. So now you call this pattern as a DDD, doublet of a doublet. So similarly, you can work out varieties of nomenclatures you can come out. And this is a situation, another example I took. I'm giving more examples because you in the chemistry class, these are all very important to analyze your complex molecules. Without doing this, it's very tough for you. That's why. So now I'm taking this molecule, proton A, coupled to the CH2. And now AM is larger. This one, it's a doublet. Then comes AY. Each line of the doublet is a triplet. Then comes AX. Each line of the triplet will become another triplet. Each line is a triplet. See, this is a doublet, and each line of the doublet is a triplet. First doublet gives you AM coupling. Second doublet gives you AY coupling. Is a second triplet. Now each line of this is a triplet like this. They have to overlap. Come on, very difficult to identify sometimes. And what do you call this one? Larger coupling is doublet, then triplet, and then triplet. It is called doublet of triplet of a triplet. Doublet of triplets. It is called DTT. Doublet of triplets of triplets. Okay. Now in this situation, consider a situation. AY is larger than AM, larger than AX. Now this is a triplet because of this is larger coupling I'm taking first. This is going to be a triplet, this coupling, and then that is further split by proton M. So it is a doublet. Each lane will be a doublet because it's a single proton. So each lane of triplet become doublets of equal intensity A. Now what happens? Each of them is further split into triplet because of CH2. Triplet. So it first became triplet of doublets. Now it is triplet of doublet of triplets. TDT. It is called in the nomenclature when you write your papers, you write as TDT, triplet of doublets of triplets. So this example is another last example. Possibly I'll give. You look at this one. AY is larger than AM, larger than AX. AY is larger than AM, larger than AX. AY is larger. This is a triplet. Then each line of this triplet is another triplet, and then it will become a quadret each line. So this first triplet gives you AY coupling. Second triplet gives second triplet is AM coupling. Now each of them splits into a quadret. 1 quadret, 2 quadrets, 3 quadrets, 4 quadrets. So when it is a overlapped multiplicity pattern, and this gives you AX coupling. What do you call this pattern? Very complex it looks. When you want to analyze the spectrum, you will see it very complex. But you have to give a nomenclature for it. There is a nomenclature name for the splitting. What do you call this one? Larger is triplet, smaller is doublet, then even smaller. So this is called larger is triplet, then triplet and quadret. So it is called triplets of a quadret. It is called triplet of triplets of quadret. It is called TTQ. So with this, I'll give you some table of nomenclature of splitting patterns in NMR. This splitting pattern is at the state of an active proton coupled to other protons. Okay. Remember, I took several examples. Don't get confused. In a given molecule, there are many functional groups. When I look at a particular chemical shift of particular proton, when it is coupled to all other protons, this is the pattern you get. It can be doublet of doublets. Larger coupling is doublet. Then smaller coupling is also doublet. It is doublet of doublet. It can be doublet of a triplet called DT. That means larger coupling is doublet. Smaller coupling is a triplet. You understand? So that is what happens. Like this, it is triplet of a quartet, larger is triplet, smaller is quartet. Like that you can keep writing. When there are three protons are coupled, three spins are coupled. First one could be a larger, it is called DDQ, doublet of doublets quartet. First coupling is larger is doublet, then second is doublet, third is quartet. If I say TTD, triplet of doublet, first coupling larger is triplet, second largest coupling is triplet, third is doublet. So depending upon first largest coupling, second largest coupling, and like that it go in decreasing order. Depending on that, you name your multiplicity like TD, TQT, TQ, QD, quartet of doublet of quartet, TDQ, triplet of doublet of quartet, like that. So this table tells you how we have to do the nomenclature of varieties of multiplicity patterns. Okay. Now with this, I'll take a couple of exercises to identify. I hope I've given a sufficient idea about how to get the multiplicity pattern, everything. Lots of examples I've given you. You must be able to follow with this. Mind you, it is a big exercise to understand and do these things. Please try yourself. It is a number of such spectra are available in books or in literature. Take an NMR spectrum, look at the pattern, start analyzing. You will get to know what is this pattern. So now I'll take a simple example for this. If I give you a spectrum like this, and I'll ask you, what is this pattern? What do you say? Look at the large coupling. Large coupling is this one. It's a doublet. Each lane of the doublet is a triplet. So what do you call it? It is doublet of triplets. What is this one? Large coupling is triplet, and each lane of the triplet is split into doublets. It is called triplet of doublets. Okay. What about this one? Large coupling is a doublet, and each line of the doublet is a quartet. It is called doublet of quartets. What about this one? Look complex? Don't worry. Now 1, 3, 3, 1. This is one quartet. One. If you look at this one, I'll put a highlighter here. See this one, this one, this one, and this one. It forms one quartet. Now I'll take a different color. I'll take this one. For example, this one, this one, this one, and this one. These four lines, 1, 3, 3, 1, is another quartet. Now what do you understand by that? Larger splitting is doublet, and each line of the doublet is split into quartets. What do you call this? Doublet of quartets. Now this one, larger splitting is triplet. Each line of the triplet is split into a doublet. See, this is a center of this to center of this is a triplet coupling, and each line of this triplet is split into doublet. It is called, what do you call this? This is called triplet of doublets. What about this one? Look at this one. This one, this one, and this one is one triplet. This one, and this one is another triplet. And center of this triplet to center of this triplet is a doublet. This is larger splitting, smaller splitting. What do you call this? Doublet of triplets. Okay. This is little complex. Let us see how to go ahead. It looks simple. It's not that complex, but we have to start thinking how this pattern will come. It looks, there is perfectly symmetric, right, with respect to this. Now, there is a way to understand. It is called triplets of a triplet. You know why? This is one triplet. This is another triplet. This is another triplet. There are three triplets overlapped. And largest value is this to this and this. Let's say any of them you can take this center of this to center of this one and center of this one. You give one coupling. Other coupling has smaller value. So it is called triplets of a triplet. What about this one? Don't get confused. Look at this peak. 1, 3, 3, 1. What is this? It's a quartet. Now 1, 3, 3, and 1. What is this? Another quartet. So it is two quartets. It is a doublet. Each line of the doublet split into two quartets. It is called doublet of quartets. What about this one? bit complex. You must try to understand these things because these exercises are, I'm deliberately taken a lot of examples for you to understand. This is doublet of a doublet of triplets. How is one triplet, and one triplet, and one triplet. It is doublet of triplets. Two doublets will be there, and then each line of doublets will be triplets. This one is little complex, but doublet of triplet of a doublet. I didn't write down how it comes doublet of triplet of doublet, but you can take this one, go out, take assignment, start working yourself. What is this pattern? You should tell me what is this pattern. Okay. So this what it is. Now we discuss lot about these things. We'll go further. Take a simple example of a spectrum like this. This is a mercury spectrum. The heteronuclear number I will not discuss. I will come to that later. But right, doesn't matter. Now this mercury spectrum. This is the molecule I am taking and looking at mercury, and this is the pattern I got. Fantastic. How do I get it? Remember, this and this proton are chemically equivalent, but it is coupled to this. There is no coupling between this and this. That's a different question because of chemical equivalence. Whereas this still mercury is coupled to these two, equivalent coupling. So when it is couplings are equivalent, what pattern we get? Initially, this will split by fluorine into doublet. This fluorine also splits this into doublet, but two doublets are of equal coupling constant. So what do you get then? Central line of the triplet, two lines overlap. So what you get? A triplet. Remember, you get two lines, two doublets. When the couplings are equal, these two lines overlap and become a double intensity. So it is 1, 2, 1 triplet. So what is that one? First one, this is the largest coupling close by. Then the second is, this is 2 bonds away, this is 3 bonds away, this is also 3 bonds away. So now first you consider 1. Okay, this is, I didn't write down. The first is the biggest coupling triplet. Then each of the triplet is split into these two fluorines by into a triplet. And each of this triplet is split by these two fluorines into a triplet. So this pattern is called triplet of triplets of triplets. TTT. It is called triplet of triplets of triplets. So this is the pattern. It is written. Oh, it is written here. Okay. Now this is one triplet, and this each is another two triplets, and each line of this triplet is split into triplets like this. Fantastic, you know. So now we look at the trifluoropropane 1H spectrum of CH of this CH2 group. Now, very interestingly, I tell you, this 3JHF coupling is larger than 3JHH coupling. These are the two coupling strengths. I am looking at this one. So, what is the pattern you are getting for CH2? Look at this one. First, it splits into a quartet, and each line of the quartet splits into another quartet because of HH coupling. So, FH coupling makes it a quartet, and this CH3 splits each line of the quartet into another quartet. Look at this one. You don't get confused. Now, this is CF3 is an equivalent CF like CH3. These are chemically equivalent group CH3. Apply 2Ni plus 1 rule. This will become a quartet. Again, apply 2Ni plus 1 rule for this. It will become quartets of quartets. How they are coming? Is one quartet, and then this each line is split into another quartet like this, another quartet, and another quartet. All lines can be assigned. This is called quartets of a quartet. Marvelous, right? So now with this, we'll give you some idea about strength of homo and heteronuclear coupling. Lot of examples I gave about how the splitting pattern comes and how to analyze everything. Now let us understand strengths of homo and heteronuclear couplings. I'll continue for this for some time. We'll see. What is the largest coupling? Remember, when I was giving you salient points about the scalar coupling, I made one statement. Strength of the coupling decreases with the increase of number of sequential bonds. I told you one bond coupling is larger than two bond coupling, two bond is larger than three bond, three is larger than four bond, like that. I gave examples. This is a general trend. Don't worry, there will be deviations in many cases, but this is a general trend. Now I consider proton. Which is the one bond coupling between protons I can think of? Which molecule? It has only one bond coupling. This is nothing but a hydrogen atom, hydrogen molecule. The hydrogen molecule, these two protons are equivalent. This and this are equivalent. When they are equivalent, it doesn't show the splitting at all. In the NMR spectrum, the equivalent spins will not show the splitting pattern. That's what I've been telling you. So it will give rise to a single peak. Equivalent spins, splitting is not reflected in the spectrum. I have been telling you. Please remember, these two are equivalent. It will give a single line. Like I said in benzene, all are equivalent. We get single line. I took methane, all are equivalent. We get single line. I get ethylene, all are equivalent. We get single line. Similarly, you get single line. But there is a coupling between these two. It is not zero. Similarly, in benzene, there are ortho meta para couplings are different. I told you. Similarly, ethylene, with all the one proton coupling to three remaining protons, all couplings are different. It is there, but still gives a single peak. Because in the equivalent spin system, I have been telling you again and again, couplings are not reflected in the spectrum. Nevertheless, we know how to measure the coupling for such spin system. Next class, I will discuss more about those things. But then, if I measure that, this one bond coupling of this HH is nearly 276 hertz, quite large. I'm writing only the magnitude, I don't write the sign. So magnitude of 1JHH is so large, the proton-proton coupling in the hydrogen molecule is 276 hertz. Now, let us look at the couplings constant in single, double and triple bond. Take a molecule like this, what you call ethane. Okay, this molecule will give rise to coupling between the protons, 3J coupling as 8 hertz. If I take a double bond, C2H4, it is ethylene. Huh? So now 3J coupling is quite large. In this case, cis coupling and trans couplings are different. One is cis, other is trans. Depending upon how, see, if I write C, here H, and here H, and here you write H. Now what happened is, this is trans coupling, this is cis coupling. Both are vicinal couplings. Trans coupling in NMR is always larger than cis coupling. Remember this point. In ethylenic molecules like this, if you write down, the trans couplings are always larger than cis coupling. So there are two types of couplings here. One is 19, other is 11. See, compared to this, double bond coupling is larger. Coming to triple bond here, it is a special case where we get 3J coupling is 9.1 hertz. Don't go by the logic. One bond is 8, two bond is 12, 18 or 12, three bond must be 30 like that. No, it doesn't go by that logic. Okay, don't apply the sequential logic like linearly I can write the coupling concept. Not possible. So this is another example which I wanted to tell you. What happens is, the coupling depends on the angle between the bonds. In this case, it's a trans coupling. Trans coupling is quite large, you see, 17 hertz, 3 bond coupling, 1, 2 and 3 bond coupling. This is called vicinal coupling. And this is also 3 bond vicinal coupling, but this is cis. Cis coupling is smaller than trans. And this is 2 bond coupling, this is called geminal, that is very small. Geminal couplings are generally much smaller. This point you must remember, this is very useful in analyzing many of the spectrum. Okay, when you are analyzing the spectra, you will understand trans coupling is larger than cis, this is larger than geminal. That is a general trend which we come across. Okay. Now in the benzene phenyl ring, if I take, you have ortho coupling, meta coupling and para couplings. See, ortho coupling between two protons in benzene is between 7 to 9 hertz. If I consider meta coupling here, this is 1 to 2 hertz. If I consider para coupling here, this is 0 to 1 hertz. So these three different couplings are present in the benzene ring. Although it gives single peak, we know how to measure this. I'll tell you later. Okay. So geminal coupling, if you come, geminal coupling 2J, generally geminal couplings can be negative. Look at this one. How do you get the sign of the coupling? I will tell later. This 2J coupling is quite large, depends upon HCH bond angle in this case. So, and also depends upon what type of substituents we have here. And in this case, it is 4 hertz negative. In this case, geminal coupling between this and this, okay, is or this one is 2.5 hertz. Like that, depends upon the substitutions, we can have the different coupling. Take methane. Methane coupling between two, you will get a single peak. But still, I said I will measure it in the equivalent spin system. I get minus 12.4 here. If I go to CH3Cl, I am minus 10. CH2Cl2 is minus 7.5. So depending upon the alpha of the substituents angle, we have different coupling strength. These are all strength of the geminal coupling. Well, we can talk more about these couplings and everything. What I am going to do is, I'll stop this today, and most likely next class I'll finish all about couplings. And I mean, maybe I can finish in about 10 minutes, but normally we should not take more than 30-35 minutes. Except, we have to stop, otherwise you will be losing interest in learning the things. Continuous lecturing beyond 30 or 40 minutes, it is a psychological study, people cannot understand beyond that. So we'll stop here, come back in the next class tomorrow, where I'll finish all about this type of coupling information, homo and heteronuclear. Then we'll really get into complex spectrum and analyze together.